So for the 221 class, we're going to focus on two basic types of motion. The first of which is going to be motion with a constant velocity. So one thing is, for motion with a constant velocity, this means that the acceleration is zero. So the velocity is not changing. If the velocity is not changing, the only way that's possible is if the acceleration is zero. And again, we're going to start by thinking about this in a one-dimensional situation where we're just moving along the x-axis. So if the velocity is constant, that means that the final velocity value is equal to the initial velocity value, and so we're just going to call that Vx, because it's what the velocity value is at all points in time. And then basically we're left with one single equation describing our object's motion. It says that the final position of the object is going to be equal to the initial position of the object plus the object's velocity times time. So what we're going to end up doing, because again we recognize that all these things are vectors, so what we'll end up doing is we'll end up breaking up these vectors into components. If we just have a one-dimensional problem, then we're just going to have a single column, just x stuff. If we've got a two-dimensional problem, we'll have x stuff and y stuff. And we'll see situations where we might have constant velocity in x, constant velocity motion in x, but a different type of motion in y. So for now, let's just think about just a simple, single, one-dimensional problem in x with constant velocity. And so we know whenever we've got constant velocity that the acceleration value is always going to be zero in that dimension. And we also know that the two velocity values in our table are always going to be the same. So this sort of defines what's going on with constant velocity motion. Now, again, this really means that we've got one equation, but it's really a vector equation. And so we're going to tend to write it as or if we write it as a vector equation, we'll write it like this. But then we recognize that this is, hey, that vector equation means there's really one equation per dimension. So this means that there's a equation for what's going on in the x direction. That's the one that we were initially talking about. But if we have constant velocity motion in y, here's the equation that governs what's going on in y. And if we have constant velocity motion in z, here's the equation that governs what's going on in z. So part of what we're going to do is when we're looking at these kinematic problems, is we're going to start by saying, what type of motion do I have in each dimension? And then that's going to help me figure out which equations I need. So if I've got a situation where in one dimension, whether it's x or y or maybe even z, I've got an object that's moving with constant velocity in that dimension, then I'm going to end up using this equation to figure out how that particle is traveling in the x or the y or the z direction. So that's the first type of motion. The second type of motion is motion with constant acceleration. So here's a situation where, again, the value of the acceleration isn't changing. Well, if the value of the acceleration isn't changing, then basically that's going to give me three equations that I can use. So there's going to be this equation I can use to figure out how the velocity is changing, because that's what the acceleration is trying to tell me. So here's the final velocity is going to be equal to the initial velocity plus the acceleration times time. And again, we're just going to start by thinking about this within a single dimension, the x direction. So this is how the velocity is changing. But I also want to think about how the position is changing. And again, if the velocity is changing, then this changes the way that I need to think about the position. So I have a new position equation that tells me that the final position is equal to the initial position plus the initial velocity times time plus 1/2 times the acceleration times time squared. So this ends up being a quadratic equation now that gives me what's going on, how to figure out the final position. You'll notice both of these two equations have time. If we solve one of them for time and plug it into the other, then I get this third equation which doesn't. So this will be useful in working problems where we don't want to deal with time. We think that we can get away without thinking about time. So these are the three equations that we have. And again, what we'll do is we'll break up our vector quantities. We'll think about their components, and if I have a problem where, say, I know what's going on in the x direction is constant acceleration, so then that tells me that this value right here is some constant value that's not 0. And then these two velocity values, well, they can't be the same, because if the acceleration isn't 0, then the velocity has to be changing. So these two values are going to be the same, and I'll use these three equations to try and figure out to solve for unknowns in this set of values in my table. So again, this is really a vector. These three equations are really vector equations. So really what that's telling me is, as always, that means I've got one equation per dimension in each of these equations. And so I can break this up into a set of three equations for the x. If the motion in the x direction has constant acceleration, or there's three equations in the y if motion in the y has constant acceleration, or there's three equations in the z if the motion in the z direction has constant acceleration. And so part of what we're going to do is basically deal with, and we'll set this up with the next video, is now that I have all these different equations, what am I going to do to try and help myself find the most useful equation to try and work some kinematics problem? And we'll talk about that next.